Hey, welcome everybody. Welcome to all of you to in a new tutorial video. So today, basically, we will start the tutorial 2. So the outline of the tutorial for today's class. Number 1, we try to understand the design flow of GM over ID technique. Second, we will try to understand how we will go to the GM over ID approach. And this is the outline of today's class. So in the last tutorial, we saw the analog circuit design using the square law models. So this is not very accurate due to modern CMOS non-idealities. To overcome this, we introduced the GM over ID technique, a practical design method based on real transistor we have offering better accuracy, and we get good amount of power accuracy and reliable performance parameter. So let us discuss the first outline, that is the design flow of GM over ID. So in the GM over ID technique, our design flow will be like this. Suppose we have some specification. Suppose we have some specification, then we will do some hand calculation. So this hand calculation comes from the simulator model libraries. So we are using a simulator. So inside the simulator, there will be some models. So by using these models, we are generating some tables or plots. So by using these models, we will generate some plots and tables. And after that, we will use those plots and table in our calculation. So we are use the simulator, say for example, like cadence. And after the hand calculation, when it will be done, we will design our circuit, and we will draw the circuit in a schematic format in cadence. After that, whenever we simulate it in cadence, so we need a simulator. So whenever we simulate, we try to compare the result. All right, so we need to compare the result. So here the main highlighting point is that the simulator have some model's parameter. This is the own parameters for the simulator. In this case, we are using cadence. So cadence have some own features, own models. So those models are used by the simulator itself, and by using these models, we will generate some plots and tables. And from the plot and the tables, we look up table, we are see the plots and tables data for our desired values. Then we will use those value in our hand calculation. So there are no mismatch chance is here. It means that the simulator and the hand calculation, the both parameter are actually comes from the model libraries. So there is no difference between the models and the plots. That means we are actually use the same thing. So finally, we can observe that our specification and our result, they are roughly very much or pretty much closer. That means the result will match with our specifications. So this is the design flow that I'm discussed for the GM over ID. So these are the design flow. Now we will see the second outline. That is how to we will go to the GM over ID approach. So GM over ID is one of such technique in which we are not using the square law. So square law, that is actually we don't use. That means it relevance all the equations, each and everything we don't consider. Okay. Instead, we characterized our MOSFET and prepare some tables or plots, and by using those plots or tables, we will do our hand calculation. So we will extract some values, and by depending on the value, we will have some equation that are not relevant with the square law, but we have some equation there. So we're just finding the values of those equation and plugging this value in the equation. So that equation will comes from our design, from our circuit, how to we actually design our circuit, how do we organize our circuit, what is the circuit diagram. So by based on those things, basically we will develop some equations. So those equations are not considerable, such as like square law. So those equations are pretty much different. They're not actually the square law equations. So if we try to design something by using the GM over ID technique, we need to generate some plots and tables. So basically we need plots. So by using the cadence, we can generate some plots very easily. So suppose we try to characterize a NMOS. Suppose we have a NMOS here, and this is the gate, this is the source, and this is the drain, and we have a voltage source here, which is VGS, the source is tied to the ground, and the body in the source is also tied to the ground. And we will consider here a drain voltage, which is like this. So this is my VDS. So for GM over ID technique, we will characterize this MOSFET in detail, and then we will find some parameter of this MOS. Like we need to find out the GM ID, GM over ID, etc. So we need to extract those value from this MOSFET by using DC simulation. Okay, so by using DC simulation. So we need a more parameter like FT, which is transient frequency of the MOSFET. We need to find out FT into GM over ID. So this parameter we need to find. Also another thing we need to find, that is the intrinsic gain. So what is the intrinsic gain? For a common source amplifier configuration, if we consider here, or like normally if we have considered no resistance, but this MOSFET have itself a output resistance. So based on that, I can write for the intrinsic gain, which is GMRO. So the cadence simulation tool didn't know the R0, but you can write that R0 is basically nothing but 1 by GDS. So if you put the value here, you get GM into 1 by GDS. So finally it will be GM over GDS. So also we need the important parameter, that is the intrinsic gain, which is GM over GDS. And then we need a more important parameter, that is the current density. So current density. So it is actually ID divided by W. So the ID divided by W is basically means that how much current available in per unit width. That means in per unit width, suppose this is my width. So this per unit width, how much current will flow? So that is an important parameter. Very, very important parameter for us. So by depending on your designer will actually extract more parameter like capacitance if you need for those parameters for your design. You need to extract the CGS, CGG, CDS, and so many capacitance you can find out by using the DC operating point. Because we will simulate this circuit or characterize this MOSFET by using the DC simulation. Okay, so by using the DC simulation. So basically the summary is that we will characterize the MOSFET in details, and we will generate some plots, and each and every plot will be in terms of GM over ID. So what does it mean actually? It means that suppose I want to plot something. So always In this case, my x-axis will be GM over ID. This will be fixed. Always we will follow the x-axis as a GM over ID. But in y-axis, we will change our parameters. Like it may be, say for example, GM. So in that case, what you called? You called actually, this is actually GM versus GM over ID. So this type of plot you may need, or either you need the GM divided by GDS. So you have ID divided by W versus GM over ID. You need to VD set versus GM over ID. You need to FT versus GM over ID plot, and then FT into GM over ID versus GM over ID plot. So all the parameters basically you need to plot against the GM over ID. So ID versus GM over ID. So the summary is that always you follow the GM over ID in the x-axis. But the happening is that whenever we do the simulation in Cadence on this schematic, let me just quickly draw it again. So this is VDS and this is your VGS. This is source, this is drain, this is gate. Okay, fine. So whenever we characterize the MOSFET, we generally do the DC simulation to extract the MOS parameters. And secondly, we will using the VGS as a sweep variable. Okay, VGS as a sweep variable. That means we will sweep the VGS, and also we will generate different curve for different length of the MOSFET against VGS. So whenever we try to do the DC simulation, normally the simulation will be done in terms of like VGS. That means in your x-axis will be VGS and your y-axis will be something that is actually the parameters of the MOSFETs. Like it may be GM versus VGS, GM over ID versus VGS, ID by W versus VGS, VD set versus VGS, ID versus VGS, FT versus VDS. So you get the plot against the VGS. So the problem is that we cannot plot the parameters directly in x-axis GM over ID. So we cannot plot this uh, against something with GM over ID directly. So we need to do some technical performance, or somebody can prefer the ocean scripting, and by using the ocean scripting you generalize the value of the MOSFETs, and you can plot your dat file by using MATLAB. So that's a solution, and another solution is available. You can plot directly everything, each and everything against to the GMO variety by using cadence. So that is also another solution. So we will see the both thing actually. All right, and if we have some alternative method, also we will maintain those things. So the main thing is that we need to uh, simulate this configuration in cadence. So whenever we simulate this schematic in cadence, we will sweep the VGS, and whenever we sweep the VGS and find out our desired parameters, so these are our desired parameters. We will find those parameters, and if we want to plot these parameters, this will be plotted in terms of like VGS. That means it will plot with respect to VGS. A VGS will be my in x-axis. We cannot directly get this plot against the GMO variety. So we need to apply here something different, and then we will generate all the parameters against the GMO variety, and after the finishing the generation of the curve, we will uh, do the parametric analysis of our length and try to find out what will be the situation for different length. And by depending on different type of length, we can easily find out our desired point in our graph, which is applied in our hand calculation to complete the design and achieve the result, which is similar as my specifications. So the main target is that to draw each and everything against GMO variety and finding some parameters and cadence. So the next tutorial segment, I will show how to generate or find out these parameters in cadence, and how to firstly, whenever we plot this parameter, this comes against VGS, and we try to interpret those plots. And after that, we will go to this parameter versus GMO variety. Okay, so up to now, everything is fine, and I think everything is understandable. So today, basically, we covered these two outlines. There is design flow of the GMO variety, and then we complete how to we will go to the GMO variety approach. So the tutorial video is now we will closed. Thanks for watching, and with these I conclude this segment. Thank you.